All right, welcome students. Let's begin by working through the warm-up problem. Get it? Working through the warm-up problem? Ha ha ha. I've already got a pun there. Let's make a drawing. It's always a good idea to make a drawing. And so what we have here in this scenario is we might imagine a point, a region we call point A. And we know that region has an electric potential of 220 volts. And then we have another region over here, which we're going to call point B. And that has a electric potential of 100 volts. And notice we have a positive 4 nanocoulomb charge, and it's going to move from this spot over to this spot. Okay. Now, questions about what happens to that positive 4 nanocoulomb charge during the move. And the first question is, welcome Joey. The first question is, what is the magnitude of the work done on the charge during this move? And so we can calculate that. If you recall, electric potential difference, delta V, is equal to the work done per unit charge in moving a test charge from one point, point A, say, for example, to another point, say, point B. And notice we want to know the magnitude. So we're going to say basically that positive, negative signs don't matter in this case. So in other words, I'm going to bring the Q, I want to figure out the work done, right? So to do that, I basically am going to rewrite this as work done equals delta V times Q, okay? And if we're looking for the magnitude of the work done, that just means I'm just going to take absolute value signs on whatever I get, make sure it's positive. So the potential difference is really just going to be the potential at point B, which is 100 volts, minus the potential at point A, which is 220 volts. And that's going to be multiplied by the charge, which is a 4.0 times 10 to the negative 9th coulombs, because nano is 10 to the negative 9. Okay? So we have 100 volts minus 220. Take the difference of that and multiply it by 4 times 10 to the 9th. And you're going to find that you get, let's go up here with our answer. We get the magnitude of the work done is 480 times 10 to the negative 9th joules. Okay? And we could basically say that's 4.8 times 10 to the negative 7th joules. So in other words, when that charge moves from point A to point B, 4.8 times 10 to the negative 7th joules of work is done. That's the amount of work done on that charge. Okay, so that's part A. Again, as usual, in the chat, please write questions if you have doubts, need clarification. Part B says, what is the magnitude of the change in electric potential energy of the charge? Well, remember, in these scenarios, the work done is equal to the change in electric potential energy. Those are pretty synonymous. And if we're talking about magnitudes, again, I'm just going to emphasize this with absolute value signs. I don't care about the sign, S-I-G-N, of the answer. I'm looking for how much. And so that's just going to be basically, hold on, I did something there. Let's erase that. So our answer to part A is the same as our answer to part B. So the change in electric potential energy, the magnitude of that change, is also 4.8 times 10 to the negative 7th joules. Okay. So we have A and we have B completed as such. Part C asks the question, how much kinetic energy has the charge gained during its move? And to kind of bring that, let's go back to our picture. I just want to make this point. If point A has a potential of 220 volts and point B has a potential of 100 volts, then most likely there is some sort of source charge. I'm just going to draw it over here. There's some sort of source charge over here that's causing the potential at A to be higher than the potential at B. So you can almost think of this source charge as kind of like a mountaintop. And as you get further away from the source charge, you go down the mountain, so to speak. So what's going to happen? If I put a positive charge at point A and I release it, what's that charge going to do? It's going to feel a force, a repulsive force, away from that source charge, and it's going to accelerate from A to B. Okay? So that's what's happening here. The work done is basically the acceleration of that charge from A towards B, away from the source charge. So you can think of this as similarly for me having a ball, say, high up in the off the ground. It has greater gravitational potential energy because it's higher up in a gravitational potential field. And then I release it. When that ball releases, what happens? It loses potential energy, but we know from our studies it then gains kinetic energy. It converts the potential energy to kinetic energy as it moves from one spot to another. So this is the same idea, but it's with electric potential energy and kinetic energy. So in this case, we can say is the change in electric potential energy is going to equal to the change in the kinetic energy. Okay, the magnitude of the change is going to be the same. And so the amount of kinetic energy that has been gained is equal to the amount of electric potential energy that has been lost. So it's the same amount, 4.8 times 10⁻⁷ joules. Okay? So there you have it. Okay, again, these concepts are not the easiest to understand. If you're having difficulty, please feel free to write a question in the chat. I can come back to it later, or obviously hit me up on Remind or via email. All right, so let's continue. We have 3 learning targets for today. The first one is I can describe the role a battery plays in a circuit. The second one is I can describe the relationship between current, electric potential, and resistance in a circuit. And the third is I can begin to see patterns in series and parallel circuits. Let's get right into it. First of all, a couple of things I want to make you aware of. I've graded and returned everything, all previous assignments, except for problem set 8-2 that was due last night. Please know that on things like labs, I still read and I make comments on them. So problem sets, I look at them, but I don't really make comments on them unless I see something. But the labs, you should definitely not only just be seeing that I returned it to you, but open up the lab and take a look at my comments. Due this Monday is the investigation that you're going to start at the end of this session today, 8-2 DC circuits. If you recall, a student named Ian Eikamp and other students have been sort of leading these Friday demonstrations outside of our school entrance. And that was happening up until obviously when school closed. Well, Ian is announcing that these demonstrations are going virtual, okay? CHS Fridays for the future. So there you have the contact information, and I just want to make sure you're aware of this. And if you're interested in that, please contact Ian and he can give you the information so you can get connected and involved. And then also this Thursday is the last science speaker of this school year. Ms. Heather Throop will be talking this Thursday, May 28th at 1 p.m. It sounds like she studies how carbon and nutrients cycle through plants, soils, and atmosphere. By the way, Spider-Woman, Ms. Greta Binford, that was awesome. I listened to that talk, as was all the talks really have been awesome. So just be aware that's an opportunity for you. Okay, so here's what we're going to do today. We're going to talk about electric potential difference, resistance, current, and Ohm's law. And then you're going to read up the investigation, and you're going to be able to collect data either individually or in small breakout groups, your choice. Just an FYI, there was no investigation 8-1 this school year. That's typically an investigation we do in class with a bunch of materials. So obviously we didn't do that. Just be aware of that. Okay, quick review for you. I'd like you to make your brain struggle for a second and ask the question, what are the equations related to electric potential difference, work, electric potential energy, and charge? And while you're doing that, I'm going to step away for a second because my dog is barking in the backyard. I'm going to try and get her back in. All right, I'm back. Okay, so here we go. Hopefully, you were able to say something like, whoa, I just remembered from the warm-up that electric potential difference is equal to the work done per unit charge, moving a test charge from a spot to another spot. And we know that the work done is also synonymous to the change in electric potential energy. I want you to remember that when we talk about circuits, which we're about to do here, electric potential difference and electric potential, delta V and V, are often synonymous. Okay, here we go. This drawing on the right here, that big rectangular thing, I want you to think of that as a battery. In IB terms, you often see it called a cell or a chemical cell. And this is a super simplified version of what a battery is. Those of you who have taken chemistry or are taking chemistry probably know a lot more about it and describe it in detail. But for our purposes, what we need to know about a battery is that a battery is a device that allows us to concentrate positive charge on one piece of metal and similarly concentrate negative charge on another piece of metal, as you can see there. And so notice we can connect those positive and negative pieces of metal via some wiring, and along the way in that wiring we can throw in stuff like a switch and a light bulb that you see there. And so when I close that switch, we're basically completing the circuit, so to speak. And in doing so, notice what happens here. You can see that there's a flow of negative charge from the negative electrode to the positive electrode. Okay? All right. Now, it's not quite that simple, and this is kind of misleading because actually charge exists in all of those circuit elements. There are electrons in the light bulb, in the switch, in the wiring that connects them. So to think of it as just all the charge is concentrated in the negative electrode and then it begins to flow is really not accurate. You can think of it more as something like this, okay? You can think of charge as being distributed in all parts of the circuit, as you can see there, because again, there's electrons, protons existing throughout the circuit. But what does happen is when you connect that circuit, it's kind of like you are holding on to a hula hoop. We would do this in class, by the way. If you're holding on to a hula hoop, the moment that someone starts moving that hula hoop, okay, everyone feels the hula hoop move, okay? So all the charge, I should say, is kind of like, basically, you can think of it as each electron giving a shove to the next electron through the circuit and causing a flow of charge that way, okay? But back in the 1700s, when we first started studying, when scientists first started studying electric circuits and batteries and stuff, we didn't know electrons. So back then, the convention was established that the positive charge that when we talked about the electric current flowing through a cell, so to speak, we always talked about it in terms of the flow of positive charge, okay? And so notice this is the convention that was established then, and we actually still use that convention today. So whenever you hear scientists, physicists, anyone talk about conventional current flow, they're talking about the flow of positive charge, okay? And by the way, that's the convention we're going to use in this course. IB uses it, AP uses it, all college curriculum that I'm aware of uses it. So when you hear what's the direction of the current flow, you need to ask yourself in which direction is the positive charge flowing, and that's the norm that we're using here. Okay, so with that in mind, let's go back, and this is a really key point, and then hopefully you recall that this slide you saw something similar here. The question I have for you is, notice there are two spots there, A and B, and I have a test charge there at A and a test charge at B. Notice there's the source charge there on the right. And my question is this: at which point at A or B will the test charge have a greater electric potential energy? Will it have a greater electric potential energy at A or at B? Take a second to think about it. Take a guess if you're not sure. If you're struggling, here's an analogy that I want to go back to. Let's say I have a textbook in my hand, and notice I have a textbook at point A, and then I push up that textbook to point B. If I asked you the question, at which point A or B does the textbook have greater gravitational potential energy? I think your answer, most of your answers, hopefully would be that the textbook has a greater gravitational potential energy at point B, assuming we're near the surface of the Earth, because it's higher up in that gravitational field, and we know the higher it is, the more gravitational potential energy it has. Well, the same thing is true in the scenario on the right here. The electric charge that is at point B has a higher electric potential energy because it is at a spot in the electric field where the electric potential is higher, okay? So notice the low electric potential energy is at A, and the higher electric potential energy was B at B. It's the same idea as the textbook. So if you ever get confused, again, think back to these analogies we've been talking about with gravity and gravitational potential energy. They can be quite helpful. Okay, so we know that the closer a positive charge is to other positive charges, it's going to have higher electric potential energy, and the further away it is, it's going to have lower electric potential energy. Okay, so now if I ask you this question, let's go back to this circuit. And we have two electrodes here. Notice I have a positive charge at A near the negative electrode, and I have a positive charge at B near the positive electrode. Which charge is going to have more electric potential energy, A or B? Well, thinking back to that previous slide, we can think that A is closer to the negative charge and further away from the positive charge, and B is closer to the positive charge and further away to the negative charge. So the conclusion we'd have to come to is the positive charges that are closer to B are going to have more potential energy than those closer to A. Okay? Positive charges closer to B are going to have more potential energy than those closer to A. So, how does this manifest itself in a battery? Well, in a battery, or in a circuit, the potential difference in that circuit is the potential energy per unit charge between 2 points in the circuit. So in other words, there's that equation again. Potential difference, electric potential difference is electric potential energy difference divided by unit charge. So notice what we have here, and this potential difference is what we commonly call voltage. So we can say is the voltage near the positive terminal is higher than the voltage near the negative terminal. And we can not only say it's higher, but in most of these cases, we can quantify it. Before I talk about quantifying it, I just want you to also think about the fact that it's the amount of work done per unit charge in moving charges between 2 points in the circuit. So when that charge moves from that positive electrode to that negative electrode, the amount of work done per unit charge is equal to the voltage, or the potential difference. An important FYI, the electric potential difference of a battery is sometimes referred to as the EMF of the battery. EMF stands for electromotive force, but that's a really bad misnomer that was used centuries ago. So I wouldn't think of it as a force. Don't think of it as a force. But when I talk about the EMF of a battery, for example, I could say the EMF of a AA battery is 1.5 volts. That means the voltage, the electric potential at the positive terminal is 1.5 volts higher than it is at the negative terminal. There's an electric potential difference of 1.5 volts between the terminals. Okay. So with that in mind, I want to go back to this analogy with gravitational potential energy. Okay. Take a moment to look at what's going on here. With this little positive charge, watch what happens here. Okay, hold on. I'm going to get my dog in my room here because she keeps barking. Hold on. Okay, so what's going on here? That chemical cell, that battery on the left, you can think of it as an elevator of sorts. And notice what it does to that positive charge. It basically takes that positive charge from a lower potential spot and it raises it to a higher potential. So let's say that chemical cell was a 9-volt battery, okay? Here's how you can think of it. You can think of it as an elevator that takes positive charge and raises its electric potential energy, and it raises it at a rate of 9 joules per every coulomb. So in other words, if 1 coulomb of charge passes through that battery, then it will have raised the electric potential energy of that 1 coulomb charge by 9 joules. If it's 2 coulombs, it would raise it by 18 joules. It's always 9 joules per coulomb, 9 volts. Okay. Now, so again, the idea here is you can think of the battery as an engine that uses chemical energy, and it takes those positive charges from low potential and moves them to higher potential. And then what happens? Those charges then are able to travel, continue traveling through the circuitry. And remember, potential difference is the work done per unit charge. So they will do work as they travel through the circuit, going from high potential to low potential. All right, who's ready for a joke? Everyone is, of course. Here we go. All right, remember, unmute your mic, laugh for a second or two, then mute it back up. What do you do with a sick boat? Take it to the dock. That was good. You got to admit, that was a pretty good one.
That was good.
All right, here we go. Let's keep talking. I want to talk about 3 concepts here. I want to talk about resistance. I want to talk about current. Well, the third concept is electric potential difference, which we've already been talking about. But resistance. Think of resistance as a way of measuring the difficulty or how difficult it is for charge to pass through an object. So, for example, something that we call a conductor allows charge to pass through it easily. So things like copper, silver, platinum, those are said to have low resistance, meaning charge flows easily through those objects with little resistance. On the other end of the spectrum, we have things we call insulators. Okay, things like glass, plastic, generally have high resistance. Charge does not flow easily through them. Okay, and those are said to have high resistance. Resistance itself is measured with units called ohms. And ohms gets the symbol of omega, the Greek letter omega, which looks like a horseshoe there. Light bulbs are one type of resistor, okay? And most commonly, you'll see resistors in circuit diagrams depicted, as you can see there on the top right. This one in the middle here, with it looks like a sawtooth, it is the most common thing you'll see in the US, like so if you have US-based books or publications. The one on the right there is more universal European, etc. So in IB problems, you're going to see this one more often than not. And notice resistors are often labeled with a number, and then the resistance value is usually given in ohms or oftentimes kilo ohms. The most common resistance values you'll see are actually thousands of ohms or kilo ohms. Resistors in real life oftentimes look like what you see in the lower right corner. They are these little ceramic-like devices. And you can see there that there are color stripes on them, and there's a whole sort of scheme, whole system that tells you those color stripes basically equate to some sort of resistance value and also tolerance in the resistance value. In other words, it's 10 kilo ohms plus or minus 1% or 5%. Okay, for you, for the purposes here, it's really important that you begin to understand and recognize the symbols and obviously the measures, the unit of measure. And there we have our light bulb. What about current? Well, current is a measure of the flow rate of charge. This is important. Sometimes I see students really get tripped up with this. So let's make sure we understand this. And so current, capital I is the letter that's given, is equal to delta Q over delta T, where delta Q is the change in charge, or you could think of it as you're standing there riverside, so to speak. If we want to use a river analogy, change in charge, it's interesting. Those are just one letter apart. And this is the change in time. You can think of it as if you're standing there on riverside and you measure the amount of water that goes by, say, a river at over a certain time period, that would be the current, the flow rate of the water. It's the same idea in an electrical circuit, but you're not measuring water, you're measuring charge. And the charge is measured in coulombs. And the time is measured in seconds. And when we measure the charge in coulombs and the time in seconds, we get a unit of measure called an ampere or ampere. We don't usually say ampere, we usually say amps, and we use the abbreviation capital A. 1 amp is 1 coulomb per second. And that's something important to remember because it helps you kind of get an understanding of what's going on. Okay, let's do a sample problem, a quick sample problem that will help us understand this topic or concept a little better. So practice problem, 30.0 millicoulombs of charge pass a specific point in the circuit in exactly 1 minute. Determine the current in amps. Okay, 30 millicoulombs. So my delta Q then is 30.0 millicoulombs, and my delta T is 1 minute. And I'm asked to determine the current in amps. So I'm going to say I equals delta Q over delta T. And I'm going to convert the delta Q to coulombs. 30.0 times 10 to the negative 3 coulombs. Milli is 10 to the negative 3. And the time has to be converted from minutes to seconds because, again, amps is coulombs per second. So this is going to be over 60 seconds. Okay, so if I do that, 30 divided by 60 is 1/2. So this would be 0.5 times 10 to the negative 3 coulombs per second, which I could make it 5.0 times 10 to the negative 4 coulombs per second, which is 5.0 times 10 to the negative 4 amps. Most commonly, you'll see people actually talk about this as 0.5 milliamps, though, in my experience. And just so you know, to give you a sense in real life, milliamps is really the order of magnitude of currents that you normally deal with on a daily basis, like coming out of your wall outlet and stuff. 1 amp of current is quite a significant current, and it's not something you usually have in your households, okay? So anyway, just keep that in mind. And Roman asked a question about sig figs. Yeah, I should probably put 3 sig figs in there. Thank you. So we'll go with 5.00, 5.00, or 0.500. All right. Here we go. Big slide, important slide. German scientist named something Ohm studied resistance of materials in the 1820s, and he discovered an important law of how resistance, current, and potential difference are related. And it's known as Ohm's law. And here's what it says. Basically, the current between 2 spots in a circuit is equal to the potential difference between those 2 points in the circuit divided by the resistance between 2 points in the circuit. And notice I said between 2 points in the circuit. So I just want to be really clear here. So let's say I have spot A and spot B, and let's say I have some sort of resistor. The important thing to realize is that Ohm's law applies to regions of a circuit. It can also apply to an overall circuit that you'll see here. But the current from A to B is equal to the potential difference between A and B divided by the resistance between points A and B. So just keep that in mind. It's applied to different points in the circuit or different regions in the circuit. And notice I can rewrite that equation as these other equations. Potential difference is current times resistance. Resistance is potential difference divided by current. Notice I keep saying potential difference, and I try and avoid using the word voltage. Again, you're going to see voltage used a lot. We talk about the voltage, 9-volt batteries, et cetera, but always try and remember it as it's the potential difference between 2 points. Okay, I think that can help quite a bit. And in that table below, I've just kind of tried to make it really clear what each of the terms are, what the units are, and what the symbol is for the units. It can get a little confusing here because the abbreviation for voltage, remember, potential difference, delta V or V, is also the same as the symbol for the unit of measure. So that can get a little confusing at times. Try and keep that straight in your mind. Okay, finally, I want to make sure you understand, begin to understand some circuit symbols. So up here on the right, we've already talked about this one, how resistors have 2 common symbols. Down on the lower right here, I want to go down to this one because this is a really important one for you to begin to understand. When you see circuit diagrams, you're going to see often called a DC voltage source. DC stands for direct current. That's not really important for us. We're going to be dealing with only direct currents for the rest of this year. If you go into HL physics, we'll talk about alternating current. But a direct current is also known as a battery or a cell, direct current voltage source. And notice this is really key. The way we draw batteries is we draw 2 basically parallel bars, but we always make one bar longer than the other. And the bar that is longer is the bar that has the positive electrode associated with it. And then the shorter bar has the negative electrode, okay? So that's important to keep in mind. I would expect you, because I won't always show you the positive symbol, and neither will most circuit diagrams. They will expect you to know that by convention, the longer bar shows the positive electrode. We have switches here. I think those are self-explanatory, just like a light switch in your house. If it's open, it means no current is flowing. If it's closed, that means the conditions are there for current to flow. Lamps. I don't really see neon lamps used that much, but you can definitely see, and you will see circuit diagrams where lamps will look like this, or oftentimes they also look like this down here in the middle. In fact, the simulation you're going to do today uses this abbreviation. And I'm going to talk more about ammeters and voltmeters when we get to talking about the actual lab, but just know that an ammeter is something, as its name implies, meter of amps, measure of current. A voltmeter, as its name implies, measures potential difference between two spots in a circuit. So just know, and I'm going to show you how you use ammeters and voltmeters here in a second in these circuit diagrams. Okay, so it's important to start internalizing these electrical symbols. Okay, so at this point, I'm going to go to the Colorado PHET investigation because I want to show you a couple things before I set you loose on it. I will keep the annotations, and we will go over here. Okay, so when you go to Colorado PHET, which you'll do here in a moment, you're going to get to this screen right here. And it says intro, it says lab. I want you to pick lab. So you're going to go into lab. And there's just a few things I want to show you about this. There are some initial things I want you to do. First of all, I want you to make sure you show conventional current. And the wire resistivity should be tiny and the battery resistance should be 0, which I think are the presets, so you're good there. And then notice over here, we can take batteries, and we can measure the potential difference across this battery. In fact, this is one of the first things you're going to need to do. Is you're going to take the voltmeter, and you're going to measure the potential difference across the battery. Notice I put one terminal there, one terminal there. Whoa! Notice I got the potential difference. Notice if I click on the battery element, I can change the potential difference across the battery. It says voltage. Again, keep thinking to yourself, potential difference. All right. Just know that I can also put batteries together, and that's one of the things you're supposed to do is put batteries together, and this is one of the first activities, and you're also supposed to change the polarity in certain cases. Those are all things that's going to walk you through. But the majority of the lab today is meant for you to actually make circuits, okay? And to make a circuit, yes, you take a battery, but then in the battery, you connect it with a wire, and you connect it with another wire. And then usually you throw a light bulb in there, and then another wire, and then another wire, and then another wire. And then actually I'm going to throw a switch in there because it's always fun to throw a switch. Okay, notice I've got set up, and when I click on the switch, boom, oh, I get a fire. That's a bad idea. Okay, I shouldn't have that high voltage. We'll go lower. All right. Oh, it's still a fire. Let's disconnect. And actually, let's make this. Actually, if you get a fire in this scenario, it's not a huge deal, but I just don't want to confuse you. Why is that such?
It's the circle right next to the light bulb.
Oh, it's not connected. Thank you. Thank you, Roman. Oh, this is great. I'm so glad I did this.
You're welcome.
Notice what I did here is I actually short-circuited, because to connect the light bulb, I have to connect the other end up here. Okay? And when I do that, it looks like now you can't see anything. That's hilarious because there's no volts. So let's move the volts back up. There we go. Awesome. So notice you have a circuit. You have the flow of current, and you have the light bulb lighting, et cetera, et cetera. And if I throw the switch, no current flows, et cetera. Now, you're going to need to create simple circuits like this, but then they're also going to get more complex. And as you do that, you're going to need to measure the potential difference across 2 points. To do that, again, you're going to measure by putting one electrode of the voltmeter in one spot and the other electrode voltmeter in another spot. Notice I got negative 10 volts there. Just know I'm looking for positive values. This is just a polarity thing. If I switch this one over here and this one over here, I'll get positive 10 volts. So we're always going to record the positive values. The other thing you have to do is you have to measure the current using ammeters. I do not want you to use this current guy here, because this current guy here is really not realistic. It's not the way real ammeters work. This is the one I want you to use. For you to measure the current with this sort of ammeter, you have to put it in series in the circuit, which means this. I'm going to take a spot wherever I want to measure the current, and I'm going to insert it in that spot in the current. So it could look like this right here. I go like that. And then I take another wire here. Boom. Okay, notice I'm measuring the current now, and I'm measuring the potential difference. The current is measured along this section of the circuit, and the potential difference is measured right now across the light bulb. Notice if I measure the potential difference at a different spot between these two spots in the circuit, notice I get no potential difference. And that is to the fact that our wires are said to have virtually no resistance. So if our wires have no resistance, which is an assumption we'll use for the rest of the year, then there really is no potential difference between this spot and this spot because the current flows easily from one spot to another from those two spots. Okay, so I think, the last thing I want to say is look down here in the lower right corner. Notice I have this battery symbol, then I have this. If I go to this, then whoa, do you see now I have symbols that look more like what I was just talking about. And I would encourage you as much as possible to work with these symbols because you want to get used to the idea of looking at batteries this way and looking at light bulbs this way and resistors. You can see the resistor right here, et cetera, et cetera. So I encourage you to do that. Okay, so the way this is going to work is in Google Classroom, the assignment Investigation 8-2 went live a few minutes ago. And there is a Google Doc there. In that Google Doc, you will see there's a link to this site. There's also a link to a Google Sheet, which is a template to collect data. So I am directing you to collect data on various different circuit scenarios, and you actually have one scenario where you get to choose and change something about the circuitry. But other ones, I've directed you to do it in a certain way because I wanted, hopefully, you to see some patterns about what we call series circuits and patterns about what we call parallel circuits. So you have a choice here. In a minute, I'm going to post the breakout rooms. And if you would like to, if you find it helpful to collect data as a group, you may do so. Please know that I'd like you to basically enter the data on your own spreadsheet. So everyone should create their own spreadsheet, copy of their own spreadsheet with their own name. But as a group, one person could maybe set this up, share it with the rest of the group, and you could go through and construct the circuits and collect data together. If that works best for you, great. If you'd like to go to your breakout room, but individually work, each of you separately on your own little simulation, but just share ideas or have questions or ask questions as it comes up, that's fine too. If you feel like you can do this and you'd rather do this on your own entirely, that's fine too. You don't necessarily need to go to the breakout room. So you have a couple of choices in there. At the end of the day, what you turn in next Monday, by next Monday night, has to be your own data sheet. It has to be obviously your own write-up of the lab. And the lab write-up is really answering a series of questions. It's not like the lab write-ups we did first semester. You'll just see it's pretty self-explanatory. I walk you through some instructions, ask you a few questions, tell you to collect some data, walk you through a few more instructions, et cetera, et cetera. Okay, so I am going to post the breakout room link here in the next 30 seconds. If you have lingering questions about anything we've covered today, feel free to stay in this room for another minute or two, and I will hang out as well. Otherwise, proceed to your breakout room and work together as you see fit to collect the data for this investigation. Okay? So this concludes the big session. And let me go ahead and get the breakout room.